Hello, my name is Sung Kim. I will be a first-year PhD student at the University of Southern California this fall. I would like to first thank the organizers of the Quantum Symmetry session of the MCA 2021 for the opportunity to give this talk. Today, I'll be talking about knots and links in modular tensor categories, and this is a joint work I've done with Colleen Delaney and Julia Plavnik. To start off with some motivation, the reason why one might care about studying modular tensor categories is because they uniquely determine a 2+1 space-time dimensional topological quantum field theory. If you're familiar with quantum mechanics, these categories provide a mathematical language to study the theory of anyons, which are quasi-particles that live in two spatial dimensions. This subject is quite fruitful in the sense that it has connections to many areas of mathematics. In recent years, the study of MTCs have been highly motivated due to their strong applications in topological quantum computing. And to rigorously define a MTC, it will take quite a bit of time. Therefore, I will only go over some of its basic structures and properties that are relevant to understand the rest of the talk. So let C be a modular tensor category and let X, Y, and Z be any arbitrary three objects in this category. We have this notion of simple objects, which I will denote the set of simple objects as IRR of scripted C. And these simple objects are essentially the building blocks for all the other objects in the category, which brings us to the semi-simple property, which says that every object in this category is the finite direct sum of simple objects. Of course, MTCs have a trivial object denoted as 1, and the trivial object is indeed a simple object, and the rank of an MTC is the number of simple objects in this category. We also have a tensor product bifunctor, which means we can get any two objects in the category and combine them together using a tensor product to retrieve back a single object. We also have these two natural isomorphisms called the associator and braid that allows us to interchange parentheses and commute the tensor product. In general, it is too strong of an assumption and restricted to say that associating and commuting share an inequality. So instead, we say that they are isomorphic instead. Of course, we cannot just choose any isomorphisms for the associator and braid, but instead we have to satisfy certain axioms. So here are two of the many axioms that we are required to satisfy. Notice that the associator and braid isomorphisms are sprinkled around the commutative diagrams, but also notice how these commutative diagrams can possibly look complicated. To resolve that issue, we have something more intuitive, which are pictures. So this brings us to graphical calculus. And graphical calculus is essentially calculus on morphism spaces, and it helps us figure out equivalent morphisms that are easiest to interpret. And the way we perform graphical calculus is by drawing these string diagrams. So on the top left of the slide, we see the graphical calculus version of the braid isomorphism and its inverse. We know that an isomorphism composed with its inverse is equivalent to the identity, and you can see this happening on the top right. For some explanation, we are essentially using the Reiter-Meister moves. The red strand is completely on top of the blue strand, so we can sort of slide the red strand to the left and blue strand to the right to get back the right-hand side of the equation. Finally, we can also represent the associators in the graphical calculus setting as seen in the bottom of the slide. We can also do graphical calculus on the axioms that I've shown you 2 slides ago. Here's a string diagram for the hexagon axiom, and you can kind of imagine wiggling these strands to get from one diagram to the other, which we can do in graphical calculus. So it's an extremely powerful tool. And as I promised in the title of this talk, we are here to talk about knots and links. So you might be wondering, how do we create knots and links in the graphical calculus setting? Therefore, I will now introduce the trace. Essentially, the trace connects the two endpoints of a function together into a loop. In order for this diagram to make sense, we do require that the two endpoints are the same object, And in modular tensor categories, the trace of a function is the special construction that retrieves a value. In particular, the value that we get from taking the trace of a function is an invariant for these categories. Now that we know how to create knots and links from a function, we will now talk about an important variant in the study of these categories called the modular data. On the left, we have the Hopf link, which is constructed by taking the trace of the composition of two braid morphisms. On the right, we have the once twisted unknot, which is constructed by taking the trace of the braid on the same object. If we calculate these values over all the possible combinations of simple objects, then we get this S and T matrix, and together these two matrices, which are invariants, are called the modular data. And so for quite some time, many experts in the field believed that the modular data is a complete invariant for modular tensor categories. But this conjecture was later disproven in 2017 by McNair and Schallenberg, and due to this, a couple of questions are raised. One of the things we are curious is whether or not there is a finite set of invariants that can classify modular tensor categories. And if so, what is the smallest and efficient set of invariants that can classify these categories? And to answer these questions, we really need to study more knots and length invariants beyond the modular data. And specifically, the first step is to understand the specific family of modular tensor categories that McNair and Schallenberg used to disprove this conjecture. McNair and Schallenberg studied this family of MTCs called the twisted quantdoubles of finite groups. Without going into the full detail of the construction and the data of these categories, the main takeaway here is that we can create this family of MTCs from finite groups with additional ideas coming from group cohomology and representation theory of Hopf algebras. And with Q is 11 and P is 5, we observe the smallest known counterexample to the conjecture. To focus on this specific case when Q is 11 and P is 5, this is a rank 49 MTC because there are 49 simple objects up to isomorphism. There are 5 categories in this family, and we will denote them as descriptive C to the U, where U ranges over 0 to 4. And up to relabeling, there are 3 sets of inequivalent modular datas. So the first and fourth member of this family share the modular data, and the second and third member of this family also share the modular data. As I mentioned earlier, we really want to have a better understanding of these categories, and in particular, the knots and links inside these categories. So we will try to do this using this technique called zesting. And as a preliminary, I will need to talk about the universal grading group. All you need to know is that for any modular tensor category, there exists a group G that we call the universal grading group, such that this category can be decomposed by a bunch of subcategories, and each subcategory corresponds to an element in the group. And what this really means is that every simple object, namely X, lives in one and only one of these subcategories. For some notation, I will write X subscript A to denote that this object lives in the grade A. Now we're ready for zesting. So zesting is this construction technique to obtain new MTCs from existing ones. The idea is essentially to change the tensor product from X tensor Y to X tensor Y tensor in additional lambda A comma B object, where this lambda AB is a special type of simple object called an invertible object that can preserve a lot of the structure of an MTC when you tensor with another object. But of course, if we change the tensor product, there are certain obstructions that might not preserve the structure and properties. So we need to make some adjustments to the associator and braid and other components of the MTC as well. The associator will become the zested associator, and this braid will become the zested braid isomorphism. And we can also express these zested morphisms in terms of graphical calculus. It turns out that the zested braid is the original braid with an additional T isomorphism that sends lambda A comma B to lambda B comma A. And this result respects all the necessary conditions for the zested braid morphism to be a braid in the new MTC. The bottom diagram shows the zested associator, and in this case, instead of a T isomorphism, we have these three co-cycle lambda ABC that handles the lambda components of this tensor product. And so the main purpose of zesting is to construct new MTCs, but we are utilizing zesting in a slightly different way. If we know that two categories are related by zesting and understand how knot and link invariants are changed under zesting, then we can obtain a better understanding of what type of information these invariants are really capturing. So one of the link invariants that we primarily studied is called the Whitehead link. Similar to the modular data, from this link, we can retrieve an invariant called the W matrix. And in a paper from 2018, it turns out that the T and W matrix together is a complete invariant for the family of rank 49 MTCs. And so this led us to investigate how the W matrix transforms under zesting for these family of MTCs that Maynard-Schallenberg studied. And so focusing on the family of MTCs that were used as a counterexample to the conjecture, we calculated an equation that relates the unzested W matrix entry to the zested W matrix entry by the scalar multiple coefficient that depends on the grade of the two simple objects and the roots of unity. And to give a brief outline of the proof, we worked under the graphical calculus setting, got the minimum braid representation of the Whitehead link, zested all the braid and associator isomorphisms to get this picture on the right, and then taking the trace and some manipulation that depends on certain knot theory properties, we were able to get back the unzested Whitehead link and some additional scalar multiples. And in addition to the Whitehead link, we spent some time investigating the three twisted knot and the Borromean rings as well. And they also seem to extract different information than the modular data and the W matrix. So the three twisted knots seems to extract information on the self braids, while the Borromean rings seem to say something about the associators under zesting. And to sum it up, different knots and links can encode different information about this category. And since this field is relatively new, we are always searching for new families of MTCs. And it is possible for none of these knots and link invariants that I previously mentioned to classify new MTCs in the future. So in preparation for that, it requires us to study more knots and links. And ultimately, knots and links are a powerful tool to understand modular tensor categories. Thank you for listening to my talk. If you have any questions or comments, please feel free to send me an email. And thank you once again.